As usual, clarifications corner. Although I guess this is more of an improvements corner, because I intend to improve my solution to the maze. So let's keep our original separate, and let's try doing a new optimized program based on this, of course. There's multiple significant improvements I missed last time, and the first one of them is the fact that I do multiple steps in here, and most of them probably fail. Now, I have already observed at this point, and it doesn't cost me anything to check before stepping. And in fact, I do check my observation, but for some reason I only decide to check my observation after I try to step. So instead, we can remove all these steps from here, like so. Yeah. This editor. And instead, we have observed, and now if we are free to move, this means jump 0 will mean that we are free to move. We will jump to label go, and we just do one step right here. And this is an equivalent program. Let's try running it. Yep, it works. So this is one improvement, and this is both reducing the amount of code in the program, and it significantly reduces the number of actions we perform, the number of ticks it takes to run, and the number of actions performed in the game, the number of turns, because this is kind of turn-based. I can do a lot of stuff inside of my program without actually influencing the game. But once I do an output, this also makes a tick in the game, in the, the robot world. So this is one major improvement, right? Once I know that I am free to go, then I go. Otherwise, I don't try to go. Second of all, is similar. We have this action checked every time. But again, we have already observed. So it is possible for us to know that we are, for example, facing an empty space. And we know that we do not need to try to open an empty space. So it is at least possible to put these actions after the checks, right? If I know that I need to go, then I can skip this action and I can go straight to the step, right? So let's do that. Wow. Like so, and like so. All right, let's test this. It's broken, but I think this should be the game itself. I noticed that this assembly editor can sometimes be laggy. No, what's wrong? What is wrong with you? Did I break something already? No, see, now it works. So yeah, that's a weird bug that sometimes seems to happen with this editor or with this game, where I'm not exactly sure what happens, but yeah, the robot sometimes just acts weirdly. So again, this reduces the number of unnecessary actions we do in the game, and it also reduces the number of ticks we take to calculate stuff, because at least we do not try an action on an empty space. If we observed an empty space, we will just reset immediately. This does still mean that we try to open every wall, right? Every time we see a non-empty space, we do not detect it with this jump, and we do try to use action on it. But really, the seemingly an optimization to this would be to actually check whether we're looking at a wall or at a door. But it just so happens that a simple action now is a cheaper instruction than an observation into a what is it? Into a decision of whether we want to action. Now, if we do, we could, in fact, bar this with a check, and I believe that would reduce the number of game turns that will happen in game, because observing and doing calculations in our brain, air quotes, does not cost us in-game time, while this action, even if it's not successful, it does cost us in-game time. But I think I'll go for tick score and simplicity. So that's probably gonna be my answer to this. That was the second big improvement. And the third is, I'd say, possibly a bit controversial, because we can significantly reduce the number of assembly instructions, so basically lines of code here, at the expense of being slightly less efficient. So you might remember how I, for some reason, got tunnel vision on subroutines and noticed that this right now observe go action is a perfect candidate for a subroutine, but then decided that subroutines would not be worth it, that calls to them and returning from them would be too expensive, and it was pointless. Well, really, all I needed to realize is that this is a loop. This should be just done in a loop. So at the very least, well, first let's start with this. We have this this unconditional jump to the start of the loop, but it's actually never reached. This is dead code, because we check all 4 directions, and because we cannot be locked in all 4 directions, because we came from somewhere, it's actually impossible for all these jumps to not happen. So this is never reached. So the kind of intuition to have a while true and a closing bracket to the while true is not actually necessary in assembly, because we have equivalently, well, the equivalent of 4 continue statements in here that will push us back to the start of the loop regardless. So that's one thing. We can get rid of that. And now we can start putting this in a loop. Now, again, since these are all the same, and at some point we will just continue, and we have to at some point find something, it's literally sufficient to just label search, or something like that, and then search unconditional jump, and all this can be removed, right? This is right now observed, go, jump 0. So, yeah, see, this editor does not seem to update the number of lines immediately. I think that might have to do with the robot braking. So at least this is possible, and this does not really lose us any efficiency in terms of what we do. Well, other than perhaps this jump, but it's not. I don't know. I feel like this is good. I haven't calculated every single number of instructions possible in here, so this might be there might be some loose ends here, but this should be equivalent. Yep. And now comes the controversial part. This is going to be a slight, definitely it's going to be a slight reduction of efficiency, but basically, if you take a look here, the only reason I cannot put this as part of my loop is because it starts with a left turn as opposed to a right turn, right? However, if instead of doing a left turn, I do wait, come again, what do I do? Yeah, I think I can turn around at the very start of the loop. So I do, for example, 2 left turns. Yeah, so here I was doing 1 left turn. So yeah, let's take a look here. I was doing 1 left turn, and then I was doing the rest of my loop, right? But an equivalent of the rest of the loop, if we're starting with a right turn in our loop, we can basically cancel out this right with another left turn, right? These two cancel out. So now it's possible to remove this, and this is our program now. That should work. Let's wait for the editor to update, and let's run it. It's broken. Is it broken because I did something wrong, or is it broken because it's broken? I think it might be broken because I did something wrong, but I'm not entirely convinced. This seems right to me. Yeah. Now it works all of a sudden, and the line numbers were correct. So that's a weird bug. I don't know, maybe it's something to do with the architecture of the PC. Sometimes when you stop it, it breaks somehow or something like that, but yeah. So we have added an extra left turn, or rather an extra left and extra right. We have added 2 unnecessary turns that cancel out at the start of every iteration, or well, at the start of every go. But this makes our code take up a grand total of 16 assembly commands. So this is a 16-byte maze searching algorithm, which I think is amazing. And it's pretty efficient. It's not bad. For a stateless algorithm, it's not bad. By the way, I did consider looking up a better stateless algorithm for searching a labyrinth, or a better maze solving algorithm than this. This is, by the way, I believe this is basically depth first search, prioritizing the left direction, or counterclockwise search, or rather clockwise search, because this is gonna be a clockwise search. So yeah, I wasn't able to find anything better than this. Maybe I wasn't looking well enough, but this, I guess, will have to be it for me. I can just watch this forever. This is very cool. 16 bytes. 16 bytes. This looks like more than 16 though. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16. What's up with these? What's up with 11 and 196? Is this because I have... No. 17? Yeah, I think for some reason it's counting these as a single line. So it's really 17, yeah. Starting from 0, so it's actually 18 total. I thought when you put 2 assembly commands it counted the line as double in this. When you put 2 commands on the same line, but apparently it doesn't. We go from 15 to 16, although between 13 and 15, I see, it's just not displaying the next one. The next one would be 17, I think. So let's just put here or something. Yeah, the next one is counted as double, so it's just a display weirdness. Okay, B star optimized .oml. Did I run out of characters? I ran out of characters. B-star opt.oml. Whatever. Alright. Now let's proceed. CPU architecture 2. I believe we're onto slowly building a new architecture. So I kind of expect to get some more wiring challenges. And I don't expect this to all be assembly. However, full disclosure, I have already seen this problem and I've spent a million years on it. Not on this exactly, but we'll get to it. So, using the instructions of your computer, read the input twice and XOR the two values together. Sounds simple, and I'm pretty sure it is. We do not have an XOR in ALU, but we do have more than enough basic logic gates with which we could implement an XOR. But this got me thinking, how did we implement the XOR at the very first level, at the very beginning when we first encountered an XOR? So if you take a look here, this was my original solution, which is pretty simple, right? We have a NAND, we have green, 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 red, and we intersect it with a red, green, 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 green to cut out the leftmost and the rightmost red with an AND, and that's how we get our XOR with two greens in the middle. But since I have to re-implement this again, I understand my new challenge is quite different. I thought I might as well try and optimize this for NAND scores. I thought maybe now I feel confident enough to actually go back to some of the previous levels and try to optimize them and possibly get the best solution possible. Sorry for the tautology. And spoiler alert, I have spent a million years on this one. I have easily spent more than an hour, maybe multiple hours, just trying to optimize this single XOR gate. Now here's the thing. There is a Steam achievement for this level that requires you to do an XOR with exactly, well, with no more than 4 NANDs. So right now we have an AND, which is 2 NANDs, I believe, and we have an OR, which I believe is 3 NANDs. So this is going to unfold to 3, 5, 6 NANDs. And somehow from this we need to remove 2 NANDs and end up with this. I already have the solution, and I think it would be a fun challenge if you are kind of playing along, if you haven't yet encountered this level or haven't yet tried to optimize it to this extent. Basically, I challenge you to try to come up with the answer, or how do you implement this in 4 NANDs? Right? How do you arrange them? What do you do here? And spoilers ahead. Now, again, I have another confession to make. In fact, it turns out that I was unable to come up with the answer to this myself. I spent a very long time just fiddling with the wires. I tried writing up truth tables for different things. I tried expressing an XOR as, tried unfolding it into ANDs and NOTs and ORs and trying to, massage it into some form which would end up in 4 NANDs, and none of that helped. But I'm not so easily deterred. And I decided, no, I'm not gonna look up the answer, but I want to solve this. And long story short, I decided to brute force the whole level using just a quick script in which I generated all possible configurations of 4 NANDs, or, well, we'll get to it a bit later, and tested what their truth tables would be and checked which configuration corresponds to an XOR. So, solution coming up in 3, 2, 1. Have you solved it yet? I sure hope you have, because it's this. Looks very simple, right? I don't know, maybe I just had some blind spot, and for some reason I wasn't able to come up with this. This is very symmetric, very simple design. At least it looks very symmetric and very simple. So, you know what? Let's try this out. This is just, by the way, I will put the timestamp if you want to skip this, but I'm very interested in this level. So what's happening here is at the end, at the output, we have an NAND. See, I'm even in monospace. Monospace? Is that the word? Font, because I was playing around with truth tables. At the end, we have a NAND of some two things, right? These two things are themselves NANDs of something. So NAND of NAND something, something NAND something, and something NAND something, right? This is these three taken into account. And what are the inputs? So at the top, as the inputs of our NAND, we have our 0, let's call them X and Y. We have our X NAND, so X NAND, and what is this? This is X NAND Y, right? So X NAND Y. And at the bottom, we have exactly the same thing, except it's not X, it's Y NAND X NAND Y. Okay. Oops. Oh goodness. Whatever. Now, do you notice something? Do you notice anything? Let's see. 1 NAND, 2 NAND, 3 NAND, 4 NAND, 5 NAND. The expression of this gate, or of this element, or of this component, or of this circuit into this kind of notation yields 5 NANDs, not 4. 1, 2, 3, 4, 5. And that's of course because this NAND, which is used for both X and Y, is reused twice. It's used in here and it's used in here. And I think that's what was stopping me from finding this in any kind of systematic way. I think this is why my truth tables didn't help me, and why I couldn't massage it into a setup with 4 NANDs. It's because this is actually impossible. An XOR is impossible to express in four NANDs like this. I'm pretty sure that's correct, because that's what my script also told me. So yeah, I guess I'll quickly talk about... Yeah, feel free to skip ahead, but this is what I did. I don't know who's gonna be able to read this, but basically we have our expressions. Since I only care about NANDs, my expression is composed only of NANDs and actual constants, such as X and Y. For constants, we have an alphabet, so that's our inputs, you know, X, Y, Z. For us, it's just 2. And we have interpretations of alphabets. There'll be, you know, X true, Y false, or X false, Y false, and so forth. So in order to build a truth table, we need a set of all interpretations of the alphabet. And what I do is I just construct all possible expressions with depth up to n. And notice that size is not important here. It doesn't play a role at all. And this is what was stopping me from finding the solution. I think this is a very interesting observation that in this kind of format, we do have only 4 NANDs. But the fact that the wire can be split into multiple offshoots, like so, makes this schematic correspond to an expression that has size, and by size I mean the number of NANDs, right? NAND, so there's 5. Is size larger than seemingly the size of this, right? It seems like we actually have an architecture kind of like this one, you know? And then these are connected to this NAND. So the extra NAND comes into play in order to not ever split a signal. So I don't know, maybe I'm talking about obvious things here, but yeah, I'm pretty sure I have tested this with size 4, and there's no, at least maybe my code is buggy, but it didn't find any possible expressions of size 4 that will produce the truth table of XOR. So that's that. I guess I'm not gonna go into too much details. So now we're done with this completely pointless digression, and we can get back to the level at hand, which, since it requires me to not to build a thing out of registers or out of components, but instead requires me to write assembly to do a thing, I really don't care about how many NANDs I use, and in fact what I do care about is how many instructions I use. So I think my solution with the NAND and OR will probably be optimal. I do have NAND, OR, and AND in here, right? Yeah, I have an OR, I have a NAND, and I have an AND. So this should be pretty, this should be pretty simple. Let's see. XOR.omu. We're still on Overture. I kind of expected to see something different, you know, to start from scratch or whatever. But apparently for now we're keeping our Overture machine. So let's add instructions for the necessary computations we want to carry out. I already have an add and an AND. Let's add an OR. This is going to be our OR. And I also want a NAND. So, hello. Okay. This is going to be a NAND. Did I add the OR correctly? I'm going to double check before I get stuck debugging it. Where's my OR? Yeah, the OR looks correct. Cool. So now we have all the building blocks. I need to read the input twice and XOR the bits of the 2 inputs. Okay. Why would I read it twice? I mean, I guess I can. So let's say read the input. Let's load it directly into B and into C. And now we can immediately, I believe, yeah, we can immediately just say NAND them. But now we have our output in D. We want to save it. So move from D to E. This is going to be our temporary buffer. We still have inputs in B and C, so we can OR them. Again, save this, although I don't need this saved anymore. I can't forget about my input already, so let's move the output of this to, well, whatever, register ABC. And let's move our saved NAND from E to B. And now all we want to do is we end them. And we out. From D to out. Yeah, let's test. No problem. 32 tests passed, XOR correct. I don't know if there's much to optimize here. This doesn't seem like a particularly important problem. Most of my time on this, air quotes, was spent by trying to figure out how to do an XOR in for NANDs. Okay, let's proceed. When do I get to start building new architecture? Are we going to build on top of byte XOR? Wait, I just did byte XOR. Okay, let's continue. When do I start to build, create a circuit that XORs 2 bytes bitwise? What do you mean? I've done this so many times. This is not even interesting. What do you mean? Where's my... Actually, I can take it from Logic Engine. Nah. I'm gonna use my old thing. Like so. I think this is more readable. I've done this so many times now. It's not even funny. Since I already have a binary XOR. And did I not unlock it? Guess I never did. Okay. Whatever you say. Done. No problem. XOR and XNOR onwards. Okay, this we unlocked, and now onto a byte constant. This looks more interesting. Create a circuit that always outputs the number 164. Well, that's no problem at all. How is this so easy? Where's my instruction thing? I want my instruction thing. Let's just go back somewhere. I don't want to create binary in my head. What did we want? 160? I already forgot. 164? Yeah, 164. Okay. So instructions, this is an easy way to 160 plus 4. So green O green and O green. Oh. Green O green, O green. Let's do this. So we want green O green O green. Yeah. Okay. No problem. I'm gonna use a not instead of an on. Although there's no way an on is more expensive than a not. Perfect. Didn't even need a tick. 8-bit constant. Okay, cool. To be honest, seems kind of pointless. Why would you want to hardcode a constant inside of your machine? Equality. Aha. Output green when both inputs are the same. Okay, this is a bit more interesting. But I'm pretty sure I just XOR them. No? What other options do I have? I have the options of negation and addition, but that's going to be more difficult than XOR. What else? Nah, I don't think there's a better solution than just the bitwise XOR. Oh, I don't have my bitwise XOR. Okay, that kind of changes things slightly. Perhaps I could do something slightly more efficient. So I was going to XOR them bitwise and then just check that it's all zeros by using a bunch of ORs. Does kind of sound expensive, to be honest. Maybe there's another way. Something involving XNOR? Well, I could equivalently go with XNORs and then fold the output using ANDs. But I think I'll just go with my gut and use XOR again. So, wrong level. Just go here, like so. Reuse this. I do need a lot of XORs though, or a lot of ORs. How did I do this? Let's do 4, unfortunate. Okay, I guess. Well, yeah, I need. Whatever. I just copied my thing from conditions. This is it. Okay, equal. Cool. That's actually gonna be very helpful for my advanced ALU. I really hope this is added as an instruction. Still, I'm a bit weirded out by how complex this looks. And yeah, this, I would probably want to... Well, I don't want to, but I think it's possible to optimize the NAND score in here, but I'm not going to. At least not now. And let's proceed. Unsigned less and signed less. Okay, this sounds more interesting. Let's start with unsigned. I think unsigned is generally easier to reason about. Create a circuit that outputs green when the first input is less than the second. Okay, so it looks like we're just implementing all the comparison operations without having to compare to 0. Right, we had our jump based on 0, or based on relative position to 0. But now it looks like we're gonna be able to do stuff immediately to immediately compare two registers. So that's cool. Inputs are movable, by the way. I'm already kind of used to inputs not being movable. All right, let's see. So I need to find out which number is which here. So if this is X and this is Y, then I need... Oi, dog! Can you hear the dog? Sorry, production quality. I need X less than 0 or Y less than X. Sorry, X less than Y or Y less than X. When the first input is less, so I need X less than Y. X less than whatever, Y. Okay, what does this mean? This means that if I were to... So all that really matters in comparison is the most significant bit. So if the most significant bit of X is lower than the most significant bit of y, then we know who's cooler, who's larger. But how do I compare the position of the most significant bit? I have a vague idea. Perhaps. What happens if I pair the bits of x and y up in such a way that we have the bits of... So this is very raw. This might be completely wrong, but just an idea. What if basically we have these piped straight into the output? All of them? Something along these lines. Yeah, actually not along those lines, but... and we only allow them to pass using bits from y, but lower. Right? So... No, this is... I don't think this is... This is not going to work because it's not actually enough to compare. What I need is the most significant differing bit, not just the most significant bit. And I don't have... Do I have some kind of directional logic gate? NAND? No, NAND. I would like a gate. Huh. Yeah, perhaps what I want is a singular gate with a pattern. So just how just like with addition, where we had an XOR, which was the primitive way to add two numbers as bits, right? So A XOR B was roughly equivalent to A plus B, where A plus B bits, or A and B bits. Right? Perhaps we have some operator. We might want to have some operator op, such that it's equivalent to A less than B, where A and B are bits. What do you think? Is this gonna... Could this be helpful? Could this be useful? So, if I were to connect them bitwise into this, I would get a bit, or I would get a byte. I would get... Oh, kind of. I would get a byte, in which every bit corresponds to... Okay, I'm pretty sure the single byte idea cannot work. I don't think it's possible to build something that performs basically a pointwise operation, where by pointwise I mean the same kind of structure we have for, you know, the basic logic gates. Where it would be. Didn't I? Well, for example, yeah, we have this kind of structure for equality, where each bit gets XORed or passes a single gate with a corresponding bit from the other byte, and then from this result we determine some outcome, some output. I don't think this is at all possible. So if I just immediately, if the only thing I do with these two inputs is I just do some pointwise operation no matter what, and just pipe them into a single byte, I don't think that can work. And why that is, I think, has to do with the fact that there is really 3 states that we actually care about when comparing these two bits. With a single bit we can encode only 2 states, but really we are tri-state. We need y is larger than x, y is equal to x, and y is smaller than x. So for example, by the way, this here, this op is, I think, should be pretty simple, right? It's just, we need, in order to have strict less, we need b to be a 1 and a to be a 0. So really we need not a and b. Just do not a and b. No, I won't. Signs are horrible. Not a and b. So this is really my op. And this outputs a single bit that corresponds to a is less than b. So if we now do this and pipe it all into a single byte, then we'll know which bits are larger in y. But this is not sufficient, because we also need to know that, so it's difficult to explain, because basically, if we start from, how does comparison work, right? We compare these two bits, then we compare the next two bits, then we compare these two bits, and so on. And at every point, we need to make sure that either, in order to proceed to comparing the next bit, we need to make sure that these are exactly equal. And with this thing, I cannot make sure that things are equal. I cannot distinguish an equality from a greater than or equal, right? This only encodes one thing. And that's not sufficient. So it doesn't look like I can do that. Now, another idea, perhaps, would be to use 2 bytes and perform 2 different pointwise operations. So I could do this for this 1 byte. I wouldn't actually converge them into a byte. I would continue doing stuff on singular bits, but just for the explanation, for the sake of the explanation. For example, for this one, I can do this less than comparison. And because I need to distinguish between equal and greater than or equal, I will also want, for example, an equality in here, right? And then, knowing that this is less than, right? This means that x is less than over here. And this means that it's, well, let's say it's not equal. Wait. Huh. Yeah, this is, I think something can be done in this kind of configuration, but it doesn't seem optimal, to say the least. Right, it's still going to be difficult because I have the multiple bits, which I will then possibly converge into a single byte, and then that byte I will do some kind of cascade of, you know, ors or ands or something in this kind of setup. But it still seems weak. Doesn't seem like a good idea. So perhaps I do want something more like addition. Perhaps I want some cascade. So perhaps it's going to be better to try to encode actual, you know, step-by-step comparison logic. How do I do that, though? So perhaps I think there might be an easier way to think about this, kind of, is, let's say I just have a default output like so. And then using these iterations, I decide whether to let the input through or to not let it through. So we'll have some switch in here, or you know, something along these lines. So let's see. If these things are equal, then I have nothing to. I have no new information. So let's just try doing something like this. So our equality would be XNOR, right? So if they are equal, then there's nothing I can do other than test the next 2 bits, right? So let's say this would, then I would test the other 2 bits, the next 2 bits, and I could switch this using the information from the bottom, like so. All right, this would be the output of the next comparison. However, if they're not equal, well, then really the fact that y is greater than x is going to be exactly the value of this bit. So perhaps this would enable my switch, but I only want this to work if they're not equal. Wow. I mean, this is looking pretty huge, but okay. Well, this is an interesting, so how about I remove this now? This is kind of an interesting setup because right now, oops. In this configuration, actually the output of this switch is going to be the value I'm after. So if I have, let me just construct some byte here. I wanna understand this is unnecessary, but I think this is just gonna be a bit easier to work with. So let's say I have something like this, and they're not equal, and my guy down below. Wait, no, actually, so this needs to be enabled by the negation of my stuff. So, well, let's just try building something like this. We can optimize later if we can. So something like this, right? If this guy is on and this guy is off, then we know that we're not equal, and if we're not equal, then the result of our comparison is exactly the value of the bit. So we let the value of the bit through if we're not equal. Okay. This seems pretty convoluted. But all right. Let's try scaling this. So yeah, as we agreed, if they are equal, then we're not letting this guy through, and instead we're going to the next comparison. Right? The next comparison happens, and let's say again they are equal. Well, if they are equal, then we do nothing. Well, we pass control over to the next comparison. But if they are not equal, then again my output is this, but I want it switched. And again I want it switched by the value of, wait a minute, right, by the negated value of this. Oh goodness, this is whatever. Like so, And actually, these guys I can just connect into a huge pipe to the exit, to the output. Okay, I'd say that's looking relatively neat, actually. It's 3 gates per byte, or per bit. Which is, well, I mean, 3 gates, but not 3 NANDs, of course. But it does look fairly simple. Could I perhaps replace this with an XOR and remove the NOT? Well, I mean, I could use a 2-bit decoder in here, or sorry, 1-bit decoder, which I believe is exactly my NOT and AND. Yeah, or NOT and nothing. So a 1-bit decoder is basically a single NOT, right? Right? Decoder, 1-bit decoder. Yeah. That's all a 1-bit, so yeah, I think that would be probably a bit more readable. So again, decode this XOR guy. And if we're equal, then go up. Well, okay, it looks better with an XOR. So if we're equal, we proceed to the next comparison, and if we're not equal, then we let through our thing. Oh, actually, yeah, over here it's gonna be 4 because of this switch enabling the comparison. Huh. Wait, but that's not actually going to work, is it? That's not going to work because this switch will not disable all the logic beyond it, and the logic beyond it will output junk signals, right? Yeah. So if I have this right now, let's remove this. I think I can create a short circuit if I wire things up correctly. That disables. I want this guy disabled. So I want, wait, oof. Okay, no, let's get rid of all this for now, for the moment. And let's redo it from scratch using a decoder. So this is wrong. We have these 2 signals. We XOR them together. And let's say we decode them. We decode it immediately. But then I choose between this, if they're equal, using the decoded signal, or I pass control up. But where do I... The question is, how do I implement this control up scheme? So yeah, I pretty much need both of the outputs of the decoder, I think. I think I need both outputs of the decoder switched themselves, which is a huge contraption. Right, I want something along these lines. So I want this, and then I want this. I know this is incredibly unclean, but yeah. So I think this is kind of what I want. Is this right now? It's pretty convoluted. It's a lot of switches for a single step. It looks neat at the bottom, But that's just because we don't have control over here. But here we need control. Let me think. Okay, I think I might have a better way. Although I'm not entirely sure, but basically over here in this higher comparison, we only have one output really, right? We only have this as our output. And perhaps if I only gate the outputs and don't care about control flow, right? So you're free to go up and do whatever you want, but so long as the output of this is unchanged, perhaps something like, oops, let's get an irregular end again for now, just right. So this will be the output if we have passed control and we're decoded. Yeah, but this is... See, the problem is, again, this will cause a short circuit because the guys up above will not know whether control was passed to them legitimately, right? Whether this thing is lying, basically, right? Because the passing of control upwards from this guy can only be enabled once this guy has already passed control. So yeah, it looks like the two switches is more of a... Well, I think an AND is probably more... Where's my AND again? Probably more readable here, but I also need an AND in here. Or, well, that is more readable with a switch, I feel. So yeah, this guy enables the control to be passed up. Okay, maybe there's something I can do with this part of the schematic. Maybe a decoder into basically two ANDs can be reduced to something better. Because I have two inputs and I have two outputs. Maybe there's a better way to arrange this? I don't see a better way. I mean, I think perhaps a decent way to lay this out would be, we have 8 switches, 2, 3, 4, 5, 6, 7, 8, like whatever. And all of them, this would be the layout of my, basically these switches, the control flow switches, will be laid out like so, and bit 1, this, will just open them all, right? Open all these floodgates. Like so. And then levels beyond will be adding switches in kind of a triangle like so. You know? This is incredibly huge and convoluted. Yeah, and I think this is unnecessary. Yeah. This might be easy to reason about, but it's actually unnecessarily large. Right, so this would be enabled, this row would be enabled if we have an equality down here, which means pass control up. This row would be enabled otherwise, or if the second bit is equal. But I think this is not necessary. I can do it in fewer gates if I just do this. But I find it hard to believe that this is really the best way to compare two numbers. seems like such a simple algorithm, but I can't seem to implement it. Alright, let me try to lay this out nicely, and perhaps I'll get a better idea once I'm, you know, in the process of trying to lay this out. Alright, I built something. I actually haven't tested this yet. This might still be broken. And a weird thing I notice is this end, which I mean, I don't actually, it looks like I don't actually need it here. Because, right, these ends, right, so we have our red line is kind of control getting passed up, and control is passed up if we have already passed control from down below, and if the previous guy also passed control from us. So I guess I could kind of yeah, I think these two lines would need to be different colors, really. So something more like, you know, come on. So this and this are different things. So the purple line tells us that control was passed from the very first thing. So it's kind of the continuation of control getting passed. And the red lines just mean that the previous guy indeed tells us that we do need to pass control up, right? So this is kind of our state. And red is the guy below us. While, yeah, and for this end, they are the same thing, right? The guy below us and the state are the same, because we only had one guy below us. So this, I understand this is completely unnecessary, but for now I'll keep it just because it's symmetric. And yeah, if we're different, then our output is the lower guy. That gets switched by this. But whether or not the different guy is actually our output depends on whether we have passed control this far up. And, well, if we have, then we encounter the next gate, the next switch, and that lets us out. So let's see if this works. It doesn't. Is 76 less than 77? It is. We get a short circuit, it looks like. So something is apparently wrong. It looks like value here 0, value here 1. Okay, well, let's not test this on complex values. Let's try testing it on smaller things we construct ourselves. So, okay. Come on. Let's first do an let's do 128. So is 128 larger than 0? Yes, it is. Yeah, this control, every guy tries to pass control up, but they don't actually need to because our purple line is off. So nothing happens. Okay, now let's add another guy. Now we're equal. And what happens now? Slightly confused here. Why is this? Oh, no, okay. Okay, so these guys are equal. The most significant bit is equal. And that is reflected where? No, that's only reflected by the fact that we pass control up and we don't actually output this. That's good. And again, we keep passing control up, but they're all the same everywhere, and so this is not even ever switched. So I think all equal numbers would be correct for us. So let's try just for the moment. Let's try doing something along these lines. Yeah, so if I just remove 2 ons anywhere, so 8. Yeah, I think we correctly identify equality with this. Well, equality as not less than. And where do we break? Let's see. So let's make these numbers small again. Oh, small in terms of bits. And let's make this guy larger. So I think this works correctly. Yeah. And I think what's probably happening is that we are unable to correctly process. No, this doesn't influence our output. Okay, how about an equality, a difference on the next? Huh. This also works. So what's the problem? I think I already saw a short circuit. Okay, here's a short circuit. Why? Does this save it? No, 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 no. Yes. Okay, so I think this should also be. Okay, that's not, but this is. I guess that's something to do with the lack of the end at the bottom. Okay. Why? What is the problem here? I think I know what's up. This chained switch setup, right, is not working. This is, first of all, this is not actually a faithful recreation of what I had in the first place. Right, my original idea didn't have chain switches, and yeah, this is just me being confused again about how a gray pin works. So, of course, this guy is enabled if I want output from here based on this, and this guy is only enabled if I am carrying up here, or I am passing control, as I've been referring to it up here. But when this guy is off, that doesn't mean that this guy will be off, right? Chaining them like so doesn't actually work. So long as this guy is unlocked, I get an output. So these two are unlocked, and this is constantly going to be a problem. But thankfully the fix for this is fairly simple. I just need to move this switch, right, from here to here, kind of. So I need to remove these, definitely. Oops. Definitely need to remove these. This one can stay, I think. Yeah, this one is effectively this. And instead, I'm gonna have... an end here, so let's say like so. So something along these lines it's gonna be, right? But I don't like how this green line has to pass under the blue, or it's the blue, the white. So I'll fiddle with this some more, and I'll be right back. How about this? Let's check. Okay, it works. Wow, that's quite the... What is this? LU? Why is the L crooked like that? LU, less on the side. That's a weird symbol for the less than operation. Okay, so this is my solution, at least my first draft. It's pretty huge, but I think it looks cool. With the exception of maybe the fact that wires are intersecting again. I hate intersecting wires. So that's a bit better. Can this be improved? So I was thinking these two ends actually only have 3 separate inputs to them, right? They have this red, they have this purple, and they have this green. So I thought maybe I could replace these 2 ends with a single triple end, but it doesn't actually seem to help, or rather it doesn't actually seem possible to implement this, because I do need to separate this green output from this purple carry up line, right? And other than that, I'm really not sure if there's much improving I'm gonna be able to do here. Well, there's definitely, of course, I can optimize this end out, and I think I might be able to do something with this because the decoder is unused. Although, this decoder only leads up, right? This is only done to carry upwards, so yeah, I can pretty much replace this decoder with a NOT, but I think just for, because the decoder is not more expensive than a single NOT. Just keep that, and this end I can just remove entirely. Let's call this red still. We'll have something along these lines. Yeah, it ends up pretty huge. A bit more compact this way, I guess. These red cables are a pain to compact because they kind of take the space of each other, you know, over here. But I think that's gonna be me. I don't feel like sitting here and trying to come up with anything better. And I would like to do the signed version of this in this video. So I expect to be able to reuse most of what works for unsigned. Less than. First input is less than the second. Yes, except now we need to be in signed mode. Right? Let's hope this is not too difficult. So I know pretty much that this entire part is still functional, right? And no matter what the other bit is, this will still compare my positive parts, the positive, you know, what's the word? Positive components of my unsigned number. And I think just based on what's happening with the most significant bit, I should be able to reuse this and just negate it when necessary. And I also want to do something with them, something special with these guys. But I think the gist is still the same. I'm gonna compare them, right? Come again, I need to implement less than, do I? Interpret the byte as being signed. The first input is less than. Yeah. Okay, so how about this? I think I might want to consider all 4 possible permutations of most significant bits here, and just take a look at what needs to happen in these cases, right? So let's go to the drawing board. Why not? So let's consider 0, 0, right? Let's consider 0, 1. Let's consider 1, 0, and let's consider 1, 1. Like so. So if we have 0, 0, then we're equal and we just pass control up. And in fact, we need to just wipe out the straight output of this, right? Because we're positive. So this means equals CMP positive. By positive, I mean positive component, which is this whole part. Okay, now if we're 0, 1, or in fact 1, 0, we are different, which means that we do not need to pass control, same thing. And the output is either this wire, this one, or it is the negation of this guy, but I think I'd rather not negate unnecessarily, and I think I'd rather just pull this down like so, you know. Yeah, except I would like to recolor. Let's do this, and then let's do this. I don't know. So this guy can't be an output if they are inverted, right? Because they're negated. So this equals to upper. Our output is upper. This thing. And if we're 1, 1, then again we're positive. Or sorry, we are equal again, but this time we are negative. And so whichever part has a greater positive component is greater. Oh, so this is just CMP. I thought maybe I would need to negate my positive stuff. So this is CMP positive. So we're actually done, are we not? I think we're done. Let's check. Wrong. Why? Oh, remove that, please, at least. Now let's try. Broken. Negative. Oh, that's why. Okay, we actually need to connect an input. Let's try now. Success. First try. Okay, cool. So yeah, this was a very simple adaptation. The exact same circuit works, except I needed to swap the most significant bit on the 2 bytes. Which maybe I could instead. I've just rewired these two, so well, I've added color to signify that they are different. I think it still can be confusing to parse this at a glance, but yeah, it's probably not worth it. I think it's probably better to keep this setup and just the color is good, but yeah, just bring this guy out like so it's clear that something weird is going on here. All right, let's double check. Done. Cool. 6 levels. That's pretty good. I think the video is going to be very long. Sorry about that. Or, I guess not sorry. Is a long video good? I don't know. I mean, there have been a million videos at this point. It's going to be many hours. So, the more content, the better. At least if it was good content. Alright. Next time, we'll go for wide instructions. Yes, finally.